Hi guys. It's pretty sad that we canceled a lab for lab 7 on that day. But here's the lecture for that day. For lab 7, the topic is about moment of inertia. What does moment of inertia mean? We can think about like this lab is a transition from linear movement to angular movement. So for linear movement, we should be pretty familiar with these two equations, right? Force equals to mass times acceleration. It's a linear movement. And think about angular movement. What is a force usually be in angular movement? Usually it's torque, right? And what does alpha mean? Alpha means angular acceleration. And here I is a mass in angular movement, which is moment of inertia. So this is the number that we need for today's lab. We try to calculate the moment of inertia in for like sport equipments. So when you think about F and M, F equals to ma in linear movement, and torque equals to moment of inertia times angular acceleration. The idea is pretty similar, right? Also, we know momentum, right? Momentum equals to mass times velocity. And when we transit it to angular movement, we know angular momentum equals to moment of inertia times angular velocity. So we can consider moment of inertia as the mass when we're doing the angular movement. Okay. How do we calculate moment of inertia? Here is a pretty classic and ideal equation. So when we're calculating moment of inertia for a point of mass, uh, we can use this equation, which is the mass times r squared. What does mass mean? Mass is the mass for this object, obviously. What does r mean? R means the distance from this point, from the center of mass to axis of rotation. So this length is r. And we doubled it, and we squared it, and then times the mass, you get a moment of inertia. But this equation is only suitable when you're calculating for a point of mass, which usually doesn't happen in real life. So what if, like, how do we calculate moment of inertia for a irregular object? We can try to find like each point of mass and calculate the moment of inertia for each point of mass, and then accumulate them together. But that's usually hard to do in real life. So here is an equation that we can use for calculating moment of inertia for irregular object. And this is the equation that we're going to use for today's lab. And it looks pretty complicated, but we try to decode it. Like ISX is the moment of inertia that we want to calculate today. And we can look at some easy things first. M is usually mass, right? So yeah, it's the mass of the object. And G is acceleration due to gravity, so it's 9.8 meter second per square. And L is the distance from axis of rotation to the center of mass. Okay, yeah, it's also a simple idea, I think. And how about this thing? It looks super complicated. T divided by 2 pi. Okay, so we're going to swing the object. You'll see it in the demonstration video later. But just imagine we're going to hang a baseball bat on on the door, and we're going to swing it as a pendulum. So for a complete swing, the time for a complete swing will be t. That means from the original place, swing here, a comeback, that's a complete swing. And the time cost for that complete swing is t. Divide by 2 pi and take a square of that. That'll be this thing. Okay, I know it's pretty hard to imagine, but just remember this equation, and when you look at next video, you should get a better idea of what it looks like. Okay, so again, we use t, which is we're going to swing it as a pendulum, and one complete swing, how much time does it cost? Is t. Divide by 2 pi square times the mass of the object times 9.8, and then times the distance from axis of rotation to the center of mass. That'll give you moment of inertia. So for today's lab, we're going to have two objects. The first object is a baseball bat, and the second object is a racket. So for a baseball bat, for each object, we're going to hand the object at the grip and also at the other end. And we're going to calculate moment of inertia when the axis of rotation is at different place. So think about it. Do you think the moment of inertia will be different if we hand the object at different end? Yes, it should be, right? Because the moment of inertia is how hard you can rotate it. It's like a mass in angular movement, right? So when you hold it at a grip or when you hold it at the other end, you don't feel the same when you want to rotate it, right? It feels easier when you're holding this end. That means the moment of inertia is less when the axis of rotation is here. And we're going to prove this concept later when you calculate it. Okay, so moment of inertia doesn't equal when the axis of rotation is different. That's the first concept. Okay, so here's the table for today's lab. We have two objects. One is baseball bat, two is racket. And we're going to hand the object at the grip and at the other end. And we're going to have 10 complete oscillations or 10 complete swings. We're going to record the total time for 10 oscillations and calculate average time for one oscillation. That'll be the t, right? That means that how much time do you need for one complete swing. And then we're going to put the t here. And here's everything you need for the equation, right? You got t over 2 pi square, mass, and gravity, 9.8, and the length, which is center of mass to axis of rotation. So in this case, say the center of mass is here, right? And when you hold it at a grip, the L will be center of mass to axis of rotation. So it'll be center of mass to the grip, which is longer, right? Comparing to center of mass to the other end. So this L is when it's hand at the other end. So you have different L, which result in different moment of inertia. So these 4 blocks is all you need for today's lab, and I think I'll get all the numbers to you in a demonstration, and you just need to put them into equation and calculate moment of inertia. All right, that's exercise 1 for this lab. Then we can go to exercise 2, which is related to parallel axis theorem. Sounds pretty complicated. You don't need to remember the name. That just gives you an idea of how do we calculate moment of inertia when we want to change the axis of rotation. Look at the equation first. Ixx is the moment of inertia about axis of rotation. So axis of rotation can change. Like you can shift it anywhere you want to. And ICM is moment of inertia about center of mass. So that means ICM is a moment of inertia when we put axis of rotation at the center of mass. Right, so that's a consistent value for each object, right? Because that's the moment of inertia when the axis of rotation is fixed at center of mass. And why is it important? Because for this equation, usually we'll get ICM, and then we can shift the axis of rotation anywhere. And it's pretty easy to calculate it. You don't need to do this. You don't need to use this equation again. You just got ICM, which is consistent in each object, and then you know the length from COM to the axis of rotation you want to shift to. and then put into the equation, you got a moment of inertia about the axis of rotation that you're interested in. So for today's lab, we got Ixx in the equation here, right? In the equation here. And then we just want to calculate ICM. So we know from axis of rotation to the center of mass, which is L here, and the mass of the object. Then we got this, we can calculate ICM. So the exercise 2 is pure calculation. I know it's pretty complicated when you just only look at the equation, but we really jump into calculation. I think it'll be better. We got all the numbers, and you know how to operate them. Okay, so this equation is for exercise 2. This equation is for exercise 1. That's all you need for today's lab. So you got Ixx in the previous table, M also, and L as well. So you got these three numbers that I'll give you. You just need to calculate ICM by this equation. And think about it. Object 1 is a baseball bat, right? And we're going to hand it at a grip and also at the other end. Do you get the same ICM in different situations? Yes, because we know ICM is moment of inertia about center of mass. So it's pretty consistent in the same object. Doesn't matter like when you change the axis of rotation, because it's moment of inertia about center of mass. It's fixed. The value is fixed. Okay, that's pretty important. Okay, so that's all the concept for today's lab. And in the next video, I'll demonstrate the data collection. And then I'll give you this table and this table. You just need to put into the equation and calculate and answer all the questions. Okay, I'll see you later.